Namaste, and welcome back to JEE Chemistry with Typical Monk. This is Class 16, Chemical Kinetics, the speed of a reaction. Thermodynamics tells you whether a reaction can happen. Kinetics tells you how fast. Some reactions finish in a flash, others crawl for years, and the difference is a barrier that every pair of molecules must climb. Today, we measure the rate, read its order from a graph, weigh that barrier with Arrhenius, and see why a 10-degree rise can double the speed, one idea at a time. Here is what you will learn today. First, the rate of a reaction and the rate law. Second, order versus molecularity. Third, the zero and first order integrated forms and the half-life. Fourth, the Arrhenius equation and the activation energy. And fifth, collision theory plus the drills, one idea at a time. 4 ideas. Run this entire chapter. Look at them together first. The rate. It is the change in concentration per unit time, and the rate law is rate equals K times A to the power X, B to the power E. The order. It is the sum of the powers in the rate law, and it is found by experiment, never read off the equation. The half-life. The time for the concentration to fall to half, and for a first order reaction, T half equals 0.693 over K. And Arrhenius, K equals RT times E to the power minus the activation energy over RT. The rate climbs steeply with temperature. Now look at the graphs, concentration against time on the left, and N of concentration against time on the right. Zero order. The concentration falls in a straight line. The rate is constant and independent of the concentration of A. First order. The concentration falls exponentially, and the rate is proportional to the concentration of A. The N plot for a first order reaction, N of R against time, is a straight line of slope minus K. And reading K, that straight N plot gives K directly from its slope, and the units of K, in turn, reveal the order of the reaction. Now the working formulas, the ones the exam turns into marks. The ribbon holds the anchors, the rate law, the first order half-life, and the Arrhenius equation. Order against molecularity. The order is experimental, the sum of the powers. The molecularity is the number of molecules colliding in an elementary step, and it is a whole number. The integrated forms. For zero order, the concentration of A equals its initial value minus kT. For first order, N of A equals N of the initial value minus kT. The half-life. For zero order, T half equals the initial concentration over 2K, so it depends on concentration. For first order, T half equals 0.693 over K, a constant. And the units of K zero order is in mole per liter per second. First order is in per second. A quick check on the order. Let us work the G favorite, a half-life and an activation energy. Take a first order reaction with K equal to 0.0231 per minute, whose weight doubles when the temperature rises from 300 Kelvin to 310 Kelvin. The half-life first. For a first order reaction, T half equals 0.693 over K 0.693 over 0.0231, which is 30 minutes. Now, Arrhenius at two temperatures, N of K2 over K1 equals the activation energy over R times bracket 1 over T1 minus 1 over T2. The data. The rate doubles from 300 Kelvin to 300 Ne. So K2 over K1 is 2, and 1 over T1 minus 1 over T2 is 1 over 300 minus 1 over 300 Ne, which is 1.08 times 10 to the minus 4. Solve for the activation energy. It equals R times ln2 over 1.08 times 10 to the minus 4, 8.314 times 0.693 over 1.08 times 10 to the minus 4, which is about 53.6 kilojoules per mole. And the lesson. A first order half-life is constant, and a small rise in temperature sharply raises the rate. Now, the picture behind it all, the barrier every reaction must cross. The reaction coordinate, it plots the energy of the system along the path from reactants to products. The activation energy, it is the barrier, ER, from the reactants up to the peak, the activated complex, and every reacting pair must cross it. The enthalpy change, delta H, is the difference in level between the products and the reactants. Here, the products sit lower, so the reaction is exothermic. Catalyst and temperature. A catalyst lowers the activation energy, and a higher temperature gives more molecules the energy to clear the barrier. Now what JEE actually asks. 5 pointers. 1. The rate law. Rate equals K times A to the power X, B to the power E. The order is X plus E, and it is found by experiment. 2. Zero order. The concentration equals the initial value minus Kt, and T half equals the initial concentration over 2K. First order, N of equals N of the initial value minus Kt, and T half equals 0.693 over K. 3. The units of K give the order, first order in per second, zero order in mole per liter per second. 4. Arrhenius, K equals A, e to the power minus Ea over RT, and N of K2 over K1 equals E, A over R, times, bracket, 1 over T1 minus 1 over T2. And 5. A catalyst lowers the activation energy, and the order, which is experimental, can differ from the molecularity, which is mechanistic. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion: the half-life of a first-order reaction is independent of the initial concentration. Reason: for a first-order reaction, T half equals 0.693 over K, which has no concentration term. Both are true, and the reason directly explains the assertion. The answer is A. Second pair. Assertion: the order of a reaction is always equal to its molecularity. Reason: molecularity is the number of molecules in an elementary step. The reason is true, but the assertion is false. The order is experimental, and it can differ from the molecularity. The answer is D. Third pair. Assertion: the rate of a reaction increases with temperature. Reason: the activation energy of a reaction is always positive. Both are true, but the activation energy merely being positive does not explain the rise that comes from more molecules crossing the barrier as the temperature climbs. So the reason does not explain the assertion. The answer is B. Now match each term to its formula. The first order half-life goes to 0.693 over K. The Arrhenius equation goes to A e to the power minus Ea over RT. The zero order integrated form goes to the initial concentration minus Kt, and the order of a reaction goes to the sum of the powers. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. The half-life of a first-order reaction is constant independent of concentration. That is correct. 2. The order of a reaction can be read directly from its balanced equation. That is wrong. The order must be found by experiment. 3. A catalyst speeds a reaction by lowering the activation energy. That is correct. So the answer to are correct. Statements 1 and 3. The trap is statement 2. The order is experimental, not read from the equation. Now the 2 mistakes that quietly cost marks. The myth: the order equals the molecularity. Read off the balanced equation. The truth: the order is experimental, the sum of the powers in the rate law. The molecularity is mechanistic and always a whole number. The second myth: a catalyst changes the enthalpy of a reaction. The truth: a catalyst only lowers the activation energy. It leaves delta H and the equilibrium completely unchanged. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. The first order half-life, if K is 0.0693 per second. 10 seconds, 0.693 over K. Question 2. The units of K for a first order reaction. Per second. Question 3. The order for rate equals K times the squared, B. 2 plus 1, which is 3. Question 4. Does a catalyst change delta H? No. And question 5. By Arrhenius, does K rise or fall with temperature? It rises. Let us gather it all in one breath. The rate equals K times A to the power X, B to the power E. The order is X plus Y, found by experiment. Zero order. The concentration equals the initial value minus KT. Half equals the initial concentration over 2K. First order. Ln of A equals N of the initial value minus KT. Half equals 0.693 over K. The units of K reveal the order. Arrhenius, K equals A to the power minus E A over RT, and N of K2 over K1 equals ER over A times bracket 1 over T1 minus 1 over T2. And a catalyst lowers the activation energy, never delta H. Next class, the solid state, unit cells, packing efficiency, and point defects. Kinetics is the story of a barrier. How fast molecules climb it, read from the order of a graph and the slope of Arrhenius. Lower the barrier with a catalyst or warm the flask and the reaction leaps ahead. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.